Hey everybody. Figured I'd go back. I'm going back through all my old projects that I did, that I've done over the years with data science, data analysis, machine learning, design, controllers. This is actually a control. This is a control project I did with like a control theory using a PID controller. Anyway, so this is hopefully this code runs. I haven't actually checked it. It's been a while. So I did this one back in 2015, sometime during 2015, like spring term or fall term, I don't remember. But it was I wanted to work with like ALS data, so that's amyotrophic lateral sclerosis. So I started working on a PID controller. So here's the problem. I kept running into all these articles, these research articles talking about how RAGT, that's robotic assisted gait training for people who've had strokes and stuff like that. They use it to retrain, like basically if you practice walking after a stroke, your ability to walk, like your recovery from it, will be much better than if you don't practice walking, right? Or lifting glasses or like picking things up. You practice, and sometimes some of your, like, you may have lost a lot after a stroke, like a lot of movement control. But what happens is if you practice doing like routine activities, what happens is you gain some of that back if you do it within a certain amount of time after the stroke, right? So this is a stroke therapy, innervation, whatever you want to call it. So basically, what I was working on was a PID controller to keep patients from falling asleep. The patients kept falling asleep on the RAGT. So it's basically a treadmill with like an exoskeleton, like mounted to the ceiling with a big giant power supply. It's like plugged in and stuff. And what it does is it makes sure that they keep walking, and it makes it easier to walk, so it's not like difficult, and it's supposed to help them retrain. Well, what happens is if the patient isn't really like motivated, or like not motivated, they're not fully rested, what can happen is while they're walking they get sleepy because the machine is really repetitive and makes it like like it kind of makes you go, it kind of makes you sleepy just standing next to it. But anyway, so what happens is that what's happening is the patients were falling asleep. So what we need to do is come up with like some way to keep them from falling asleep. So what I came up with was this PID controller. It basically just like kicks in, and like I wasn't sure if I was going to use a light or what, but when they start to get like every certain amount of time randomly, it will turn on a light. Or another thing is it make a noise, but that was like too startling. You don't really want to startle people when they're like, you know, really getting into the zone or whatever, because it's just kind of annoying, right? So like a light or like different patterns and stuff. And what happened was as they walk, like if they started to slow down, or after a certain amount of time, if they started to slow down, it would count up like a certain window. And when it reached that, if that window had a certain number of times that it decreased, then when the velocity decreased, then minus obviously all the accelerations, like, or increasing velocity. So what happened was the treadmill would change speed, right? So it'd speed up to keep them like speed up and slow down, and it had like kind of like a mountain shape, like where it went up the hill and then came back down for the like duration of the amount of time that they were going on the machine. So like I think it was like 7 or 8 minutes. I don't remember. I got all the data. I had to go through and get all the data from different research papers about like how fast a normal person is, how fast, like how, and I actually mapped in the footprints. So that was the other thing. There was a foot sensor. They had a foot sensor on, and both their feet. So when they'd step, when they were doing this, the foot sensor would tell how quickly they were stepping, right? And so if they started slowing down while the treadmill was going, it would slow down the treadmill so they wouldn't fall, right? Or like if they weren't using the RAGT, but not using the robot assistance, but basically keep them from slipping. And it slows it down and it speeds it up based on how their walking was going. And so then it would increase, the speed of the treadmill would increase along that mountain pattern where it goes up and like increased speed, and then comes back like 2/3 in, it reaches its apex and it starts coming back down. And it had different patterns, but basically what this specific controller was for was to match the treadmill speed to how they were doing. Basically like it was like a feedback system to like check to see how close they were to like basically keep the treadmill matched between the person and the pattern, the path pattern that they're following, how fast it goes over time, as it builds up to 2/3 and comes back down. And so it was all built off of what they could handle, like the max speed and stuff. So I set it like 12% or 20% below the max speed. But anyway, what it does, it basically builds up, and then I have all these PID controllers, like running through a PID controller. And then it would do all that stuff. It was pretty cool. I'm gonna run it real quick and see what it looks like. I don't know if it'll run. I hope it runs. I hope the data's still there. Oh, we got warnings. Badly conditioned. Wonderful. So here's the mappings using it. So what I did was to test it. I actually came up with a like in silico. I think that's the term. I'm using little air quotes. In silico patients to test it because I didn't have like at the time I didn't have my live patient training or whatever. I didn't have my certificate for that, so I couldn't do it for real. But this is what it was doing, and so that's the this is the treadmill speed thing. So this is up to 30 minutes, but you could this had different there were different patterns. This is the longest one, so the 30-minute one it was for testing against a real like a what do you call it fully healthy person, not a person who had a stroke. But basically this is the velocity. It goes up and down, and this is all mapped off the thing. And there's actually I actually have somewhere in here. I don't know if it's here. Oh no, it's not in this version of it. This is a different part of the controller. Another part of it had I had actually mapped it to actual people's footsteps based on actual sensor testing to build so that there's actually step, and it's actually following the actual gait of an actual person during an actual test run. So I actually have the real test data for that. I gotta stop swinging that around. It's so fun to swing around. So this is all mapped. This is the controller trying to match to the actual person's walking speed on the routine. And so you can see how close I got it, but it's just badly conditioned. Anyways, this is like it was pretty fast, so like you could almost do this in real time, but it was a little bit slow for real time. That was the big problem. But nowadays, like I'm sure that you could get a lot more powerful with a computer because this was 3 years ago, 3.5 years ago. So now it's like a lot faster. So this is what I was working on at the time. I was really into RAGT and the robot assisted gait training and like all the the robotic orthotic. They're not prosthetics, they're orthotics. Like the braces and stuff that help people move, or like they have these wrist ones that help, like they have cables in them and they help or rubber bands or whatever, and they help you grip your hand, like use your hand because people shake. Some people have disorders where their muscles send a lot of signals, but the signals don't stack up. The signals from the brain don't stack up on the nerves. They instead of adding up to a whole, like you grasp something and hold it, what happens is they shake because they get like intermittent signals rather than just one signal to grip or one long signal to grip with a whole bunch of action potentials, and so they get a bunch of like separated ones. And what happens is, so this is what I worked on. This is what I came up with, and it actually worked pretty well, as you can see by here. And I think the error was like pretty low, but some of the other models were not as good. This is the first part of the path. It's this part right here. It's this part right here, and then the second middle third right here, and it reaches the apex. So it has two apexes on this one, but this is for like a healthy individual. No disorders, no nerve problems or anything. And so then this comes back down, and this is like that, and this is in silico because it's just showing what a person would actually do based on my using the map, the patterning that I came up with from the thing. But I actually have other data that's not this. This is just like to proof of concept type of thing. And I went a little bit further with this than this. This is not the completed thing. But anyways, I had one that was shorter. It was like 7 minutes. I'm not sure where the code for that is. It might be on a different computer. But this is 7 minutes. Or the original one was 7 minutes, and it's just like that's or 7 to 15 minutes. I think the average gait appointment or gait therapy appointment is like up to 30 minutes of actual training time. So you can see why people will get sleepy during this. Like if it was just like flat, like the treadmill speed was flat, or it had a slight up and then a slight down, like flat, like not curved. This is much more like indicative of like you're walking in a park or something. So as a slow warm up, it takes about 2 to 3 minutes to warm up to reach the peak speed, and then it goes. And this is actually, I think, if this is not the right one, I'm not sure, but I can't remember. But I think 1.6 meters is actually the speed of. It was based on I used a bunch of data, and I went through and I did linear regression on it and got like average times from a whole, like massive, like, well, not massive, but a whole bunch of data sets. I took a whole bunch of data sets for people without any disorders and their gait, and I took a bunch of data from a bunch of people with like ALS, and I took people with stroke recovery, and I took all that data and I linear regressed it and found out what the ranges were and the standard deviations and all that stuff to figure out those things. And so this is the data I actually got. And then as it mentions up in the code, there's a, what do you call it? I have let's see, here's the whole thing. That's all the data just for this one. This is not very big of a data set, but that's like This is not the full time set. I think the time series for it was like a lot bigger, but this has been simplified or shortened down. I chopped it down during my processing. This is the third version, and there's a second and first version here, and I think I had a fourth and a fifth and a sixth version because I just kept like expanding out. But this is just proof of concept to get it going. Quite a bit further with it, but this is pretty good. Yeah, this is a fun project. And then the idea was if you could keep the patients from falling asleep or getting sleepy on the treadmill while using the RAGT, they would have improved outcomes because that was the big problem was they were falling asleep or they weren't. If you're not like pushing yourself to the limit basically, or like pushing yourself above what is comfortable, and some people don't know where that level is. If you're not pushing it past that with this type of training, you don't have as good of gains. Like your improvement and your recovery and your restoration of function is not as good, or at least that's what the studies were saying at the time. And so, how could they fix that? And this was one of the solutions that I came up with for that. Anyways, thanks for watching.